next, and last but not least for this session, we have one of the, I guess, maybe the only presenter here.
I will say that.
Okay,
yeah. Don't steal my joke.
I'll let you take it. So Matheus Grasselli from McMaster University, he's going to tell us about climate change, finance, and macroeconomics. So Matheus.
Thank you, Sebastian, and thank you, the organizers. And as Sebastian was saying, I am the only known local person other than Bruno who has been to all of the 13 events here for this conference. So I hope to continue this perfect record. And so every year is a happy moment when I receive that email with the invitation, and I try to reply very fast so that they don't change their mind. And so this year I got it, and within 30 seconds I sent a message back to George with a copy to Bruno saying that I wouldn't miss it for the word, and I meant it. And no, I don't care how many anniversaries of the Black-Scholes equations they are celebrating at the same time. In what obscure Middle Eastern country I would come here. So this unfortunately also has nothing to do with Bruno's work, but I hope that at least you will find it interesting. Is a talk on climate change, finance, and macroeconomics. If you've been following the talks that I've been giving here, the scope of the talks is increasing progressively, so now I'm going to talk about climate change. And so it's a joint work with several people, some at McMaster University. Emma Holmes and Daniel Press are students. Ben Bolker is another professor with expertise in ecology and climate change. And then the second line are people working at the Agence Française de Développement under Gaël Giraud, who is a co-author of mine in another publication, but he's also the chief economist of the AFD. And at AFD, they are doing this large-scale models that we're going to be talking about, and they use a lot of the work that I had done before in macroeconomics. So Gaël decided to join the efforts of the groups, and we're trying to do an extension that I'm going to talk towards the end of the talk. So I'm going to spend most of the time describing what the approach is about and some of the preliminary results obtained by this group, and then towards the end focus on what we are currently doing. The combination of climate change and economics go under the name of integrated assessment models, IAM. And early models like that, going back to the 1970s, they focus mostly on given the economy as it is, see what the effect of economic development is on climate and on the planet. The most famous example in that line is what's called the limits of growth. People in the know call it the LOG work. And it was done by this group, the Club of Rome. So this convened in Italy. They had been working for many years before. They were commissioned. So there was a large team, about 30 scientists and economists, mostly at MIT. And their approach was to run large-scale computer simulations under what's called systems dynamics. Whenever I say that I do dynamical systems in macroeconomics, there's always an economist that says, oh, that's like system dynamics. I said, no, it's a permutation of the words. It doesn't mean the same thing. So systems dynamics sometimes use dynamical systems and ODEs, but they use a lot more. They use agent-based simulations and other techniques. Jay Forrester was the guy at MIT that popularized this approach of systems dynamics, and this integrated assessment model was one of the early examples where they used it. What did they do? You know, we're going to see a couple of the diagrams for where these things get integrated. So part of the book was to run a simulation with what they call business as usual, or the standard run. So without any changes in policy or technology, they just looked at things like, when are we going to reach the exhaustion of natural resources? And when those resources finish, well, there are some inputs to production functions. So then what happens? What happens to growth, and what happens to population? Because population needs to eat food and that kind of thing. So the key prediction is that the business as usual would lead to sudden and uncontrollable decline in population and industrial capacity within the 100-year span from 1972. But that was not the only prediction of the book. They also looked at alternative scenarios, so with changes in technology and with changes in policy, what could be done, and they were showing that, you know, it's not all bad news. You could have alter dynamics that don't result in a collapse. This was universally criticized. It's rare when you have a work that can be criticized from left and right. I tried to do many papers like that. I presented here last time. There's negative interest rate models. I told you they're criticized by left-wing and right-wing economists. So this was another work like that. Was criticized, of course, by industry, by trying to put limits to what they are doing. Criticized by economists. They had a few economists in the team, but the majority of the people in the team were natural scientists. But economists criticized for not introducing rationality and enough decision-making in the model. Criticized by the Catholic Church because it implied population control. And then, not unsurprisingly, criticized by the political left because, if you remember, this 1970s, many countries were trying to implement kind of redistribution policies that depended heavily on continued growth. So if you take growth out of the equation, those policies don't work anymore. So this was seen by those leftist governments as saying, now you're saying that we cannot implement these policies and need to leave, the proletariat at misery as it continues to be. So this is a picture of, they progressively build up the models with more feedback loops and so on. You cannot read what this is, but this is just to show you, each of those boxes is kind of a module that is either a differential equation or a simulation, and then you need to integrate all those things and do the predictions. So for example, this. It's what, sorry?
It looks like adjustments to supergravity.
Of course, yeah. I told you, this is a very narrow talk that I'm giving. The topic is very narrow. This is one of the predictions, and if you can try to memorize, or the important thing in this picture is this industrial production per capita at some point, I don't remember which one. Yeah, it's this one here. It collapses, and population at some point collapses down again. And pollution eventually collapses because you stop producing things. But this is type of the outcomes that were there, and that was the standard run. That was the business as usual. So try to just memorize this industrial production going up and then going down after, more. This was starting in 1900. This is 2100. So this would be about mid-century, a couple of decades from now. More sophisticated integrated assessment models are the type that use sophisticated economic models at their core. So now you put more of, utility optimization, decision-making, optimal rates of production, optimal rates of carbon pricing, and so on and so forth. And then try to see if the economic agents will adjust their behavior by knowing what the effect of the economic development is on climate. The most famous example here is DICE, so this dynamic integrated climate and economy model developed by William Nordhaus in 1992. Now, by having this economic decision core, it relies on all the tools of macroeconomics, mainstream macroeconomics, dynamic, stochastic, general equilibrium models, welfare maximization, general equilibrium, sometimes partial equilibrium, and cost minimizations. And for example, DICE relies on a production function of Cobb-Douglas type, and agents' decisions are made with infinite foresight. So you need to look far into the future, infinitely far into the future, and then discount back to the present. And this type of models, because of this infinite foresight and rationality, they don't have as a built-in feature things like economic collapse or over-indebtedness, which are things that we're going to see in the alternative models that I'm going to present. One other outcome of these models is that there's a sort of oversized importance of the discount rate, because if you have to discount everything to present to do your optimization and your optimal decision, then of course, first of all, you need to have consistent discounting, so most people use exponential discounting. It's very hard to do hyperbolic. Lane has worked with doing time-consistent hyperbolic discounting and infinite time horizons. It's more involved, but can be done. But if you do exponential discounting, then what happens is that small changes in the exponential rate will make all the difference between doing some green technology projects or not, because that will make huge difference in how you discount the cash flows in the future. Well, needless to say, I don't like that kind of approach because they have a very hard time integration with the rest of the approach, or the rest of the climate models. So there's a fundamental mismatch. It's almost ontological. Now I say that every time that somebody mentions ontology in a talk, I reach for my gun, because that's typically some historian of economic thought or a philosopher of economics making some rant about the use of mathematics in economics and how inappropriate it should be. But in this case, I claim that it is an ontological problem, because the type of adjustment processes and dynamics that you see in climate models, as we're going to see soon, they depend on disequilibrium and gradual adaptation that it doesn't fit with the economic models. If you have done DSG models, you will know that the type of dynamic stability that is required is the type of saddle path stability, that as soon as you deviate from the saddle path, then the agents will project that you're going to some infinite trajectory from some variables, and they will instantaneously adjust back. So you do that in economic models by adjusting your expectations about interest rates, inflation, or other parts of the model. But it's very easy to adjust expectations. You just say, oops, I was wrong. Here's my new expectation. But try to do that with climate. You cannot adjust the carbon cycle, and you cannot adjust radiative forcing and so on just by changing your expectations. Is that the time left or the time gone? Oh dear. If you compare limit to growth with data, you see that it compares quite favorably. These are some other trajectories that they had in the book, but the important one is the business as usual, the green one, the standard run, and then the purple dots are data, 30 years of data. So the sort of unsophisticated limit to growth model actually had kind of a good 30 years after it was published, and now it's 40 years and it continues to do well. Meanwhile, the sophisticated DICE model hasn't been around for too long, but what you can do is go back. After all, it's supposed to be extended for 100, 150 years, so you can do cross-validation. You can go back to the past, calibrate the model to up to, say, 1920s, and then run it and see what happens. And these are the 5 and 95 percentile, and the actual trajectory is completely outside that. So naturally, between a model that is unsophisticated and does well, and a model that is sophisticated and that does badly, the economists preferred this second option, and they gave a Nobel Prize to Nordhaus. What I want to show you is a different way of doing that by replacing the core DSG model in those integrated assessment models with a stock flow consistent model. Now, you might have seen different talks of mine on this subject. So the stock flow consistent models start with a table that looks at the flows between the different sectors of the economy. So this is a standard macroeconomic table, but the only difference here is you can't quite see, but it's this damage function that is what comes back from the climate model and feeds back into the economic model. Now let's walk through the steps of this model and then show some conclusions. So basic definitions, I follow standard economic notation as much as possible. I know there's a lot in this slide, but I'll try to walk you through it. So the important thing is output. So output, in the absence of climate, is something that comes from how much capital you have. It has a capital to output ratio relationship, which is here. But with the climate damage, then the potential output gets reduced. You don't have you don't produce the potential, you're going to have some damage, and pay attention to that damage function. So it's a reduction to output. And in addition to that, there's a further reduction because part of your output needs to be used for abatement. So abatement means retrofitting your factories and your houses and so on so that they have less emissions. So that's not something that is consumed, that has to be subtracted from output. Everything else is standard, in particular the dynamic variables of the system are the wage share, the debt ratio of the private sector, and the profit ratio profit ratio of firms. The other thing you should pay attention here is some dividend payments that are made from firms to the private sectors, but that's a difference from the standard model. It has to be modified a little bit, but I'm not going to talk too much about it. The differential equations for the economic model then become the same differential equations that we have in the keen model that I explained here in this conference a couple of times, but again, with the addition of this damage function that now modifies many things. And the other thing is that the population dynamics here is assumed to be some logistic population dynamics, because this is really what, you know, UN projections of population is. The population is going to continue to grow, but at some point, not in the distant future, is going to plateau. Now comes the climate model. So it has 4 pieces, and I think I have time to explain all of them before the pictures. So the first piece of the climate model is emissions. So emissions come from 2 sources in this type of simplified model. You have land emissions, and this is from deforestation, and for everything that is not related to industrial production. So that's the part that you don't control as an economic agent or as a firm in the model. So that comes from outside, and the assumption is that land emissions go down. So this is a negative rate because of improved technology in general for carbon capture or for, you know, doing something with reforestation and things like that. So that goes gradually down. But the emissions for industrial production is the thing that you can more immediately affect. So that comes here. So it is given by your output, but then multiplied by a carbon intensity in the economy. Yes?
My understanding was land emission was precisely there was a feedback loop. For instance, you know, the fact that the ice on the Greenland is melting, you know, is making on the contrary. I mean,
so that's the part of the model. Yeah. That's the part of the model that comes with when the temperature gets to a very high ranges, when you have more nonlinear feedbacks that you account here. So this is not accounting for that yet. Okay, so it could be worse. But this is like the that's the optimistic part of the model. Now, industrial emissions have to do with output, but multiplied by some carbon intensity. And again, this is an optimistic view of carbon intensity, that because of the increase in technology, the intensity of the economy goes to 0. So eventually, you're going to reach some sort of a carbon shift where no matter how much output you have, emissions are going to be reduced to 0. But then in between, you can try to reduce the emission rate of the existing production. And this reduction in emission rates is something that has to do with an arbitrage between the price of carbon and the price of the backstop technology. So the highest the carbon tax that you have compared to this abatement cost is how much you spend not to have emissions. So you just make a competition between those 2 terms, and this is the choice of emission rate that the firm is going to make. Okay, so that's the emissions module. The output of these modules is this total emissions, and that enters the carbon cycle. So the carbon cycle is how carbon enters in the atmosphere, and there's 3 layers. So there's the atmospheric layer, then there's the interaction with the upper layer in the oceans, and then there's the deep ocean layer, and that's the minimum thing that you need to model. But emissions only enter here through this top level, and then there's some matrix here that kind of mixes up depending on some proportions, and the idea is that even after you stop emissions, it's going to take some time for things to go to the sort of pre-industrial relative concentrations, but eventually they reach that. Now, so the output of this is the carbon concentration in the atmosphere, and that enters the next module. Because the highest the carbon concentration, the highest what's called radiative forcing. Now, radiative forcing is the difference between what remains in the atmosphere and what is sent back to the universe. And the highest, well, we're going to see in a second what that does. But the point is that when you increase the carbon concentration, you increase the radiative forcing related to industrial emissions. There's another radiative forcing that can come from other effects which are not related to carbon. So these are the greenhouse gases and some other effects. Now, so again, the output of this module is this radiating forcing that then enters the final module of the model, which is the temperature. So the highest the radiating forcing, the more is captured in the atmosphere, the temperature increases. And again, it's a 2-layer system. You have the temperature in the atmospheric layer and the temperature of the deep ocean, and then they sort of there's a convection in there, and then this determines what the temperature, average temperature of the atmosphere is. Why is temperature important? Because then it feeds into the damage. Now, damage is anything that temperature causes to both output and capital. So this is total damages, and it's normalized, calibrated in one run of the model to what Nordhaus has in his DICE model. And this can be divided into part of it goes directly to output, and part is attributed to damages in capital. So your factories, they kind of rot, and then you cannot make stuff. But also after you make stuff, stuff gets damaged because of damages to output. These are alternative forms of the damage functions. They are more severe forms. So this has more convexity. And then this is a damage function that in addition to affecting output and capital, it affects productivity. So it's not only your final product, but you get kind of slower because of temperature. Your productivity is not so great. So these are some graphs of damage functions and temperature increases. The Nordhaus is the most optimistic one, and then this Weizmann is intermediary, and then this Stern function is the most severe. Now, so let's do a couple of runs of the model. The first one is with no feedback. So that means just the economic model pretending that the climate is not there. And then you calibrate the model just to see if for economic reasons alone, because this is a model that allows you to go to explosive debt and all the bad things that I've been talking along the years, just the economic reasons. So you see if without the climate, the economy is in a kind of stable trajectory. And what they find, so this is part of the team that we're working with, is that yes, so this is for the employment rate and wage share, and this is real growth rate, it stabilizes. This is output has increased and exponentially, and then emissions increase. Now, the next thing that you do is just investigate the kind of static effect of temperature. So not do the whole temperature dynamics, but just assume a final value for the temperature. Just after it's all done, let's just pick this final value, see what the damage function is, and go back to the economic model. And this is what you can see here, that as you increase the temperature, gradually, the final equilibrium gets progressively worse in the sense that this is employment rate and wage share. You get smaller and smaller employment rate and wage share and higher debt ratio, because this is combined with this private debt, until you get to a bifurcation point where around here, which is around 3 degrees increase, it's not like that. It goes suddenly to zero employment rate and wage share and sort of explosive debt. So that's the kind of range that you don't want to be. This runaway effects start to play a bigger role. But that's only for the equilibrium, the static. We want to know now the transition. What's the dynamics that leads to that? So you can see here, you can't read the legend, but there are different shapes of the damage function. The only one that continues to grow is the no feedback. Any other damage function with either the Nordhaus or Weizmann or Stern calibration eventually collapses. It might take longer, 2200, or it might be at 2080 or whatever, but it's not a question of when, of if, it's a question of when this collapse happens. But this is with no policy, so it's kind of the standard run of the limits to growth, but in different scenarios of damages. Now, what you can do also is two things in this slide. There's a sensitivity analysis, because many of these things have a distribution of values for the parameters, like the doubling of the radiative force and with, the increase in radiation force and with doubling CO2. You might read about this as the key parameter in climate model is the climate sensitivity of the model. So you can put distributions on those and then run. So here the basic things are these 3 lines is blue, red, and orange, and it's with no policy, with only a carbon tax, and with a carbon tax plus a subsidy. And the blue one is the carbon tax with a subsidy, and is the one that performs better in the sense that you have some chance of maintaining your temperature anomaly around the 2 degrees Celsius that the Paris Agreement identifies as the point where we should be aiming at. And then, things where you have a carbon tax but you don't have subsidies, then you might have an explosion of private debt, which is also not good, because that just means it's too expensive to handle the carbon policy, so you need to have some government subsidy to help with that. Now I spoke too fast, and I'm close to the end of what I need to present. Let me remember if I missed anything. No, I think so. So this is all combinations of what this other group did and what we are doing. Now I want to tell you very briefly about the extension. So when we said, okay, let's collaborate. So what do you want us to do that you haven't done and find really, really important? And they said that the most important thing for them is an extension of the global model. So there's a model for the entire economy of the planet to, of course, the ideal would be a regional model. Nordhaus has a version of DICE, which he calls regional integrated model, so it's RICE. So we have Arch and Garch, they have DICE and RICE. So that would be the ideal when you have many different regions, but it's already a very good thing if you can do just the rich north and the poor south, and then see how the model needs to be changed, because it's not everything in the model that can be compartmentalized, and now you just double the size of the variables and have some interaction terms. Some things cannot. For example, the atmospheric layer sort of homogenizes very fast. In a matter of hours, the carbon concentration in the atmospheric layer is indistinguishable in different parts of the atmosphere. So clearly you need to have only one component there. The average temperature for the globe is only one component, but there are things that you can have different. For example, north and south will have different productivities, different capital to output ratios. Their behavior in terms of investment and consumption is going to be different. This opens up a whole can of worms that is not in the original Keene model, but it's some stuff that I worked in an extension of the Keene model with consumption, that then you need to work with disequilibrium of supply and demand that creates another cycle in addition to the original cycles that were there. Disaggregation damage functions are very important, because the damage to the south is presumed, and in some empirical papers estimated to be much larger than the damage in the north. And now you need to think, so it's not just a question of, so what do you do? Oh, well, so there's an exchange rate mechanism that connects the two economies, but then you need to think about policies. So are you going to have a uniform carbon pricing all over the world, or are you going to have differentiated carbon pricing in different regions of the world with different policies and achieving decarbonization at different rates? You need to think about subsidies and cooperation. So yes, the North needs to pay a lot, transfer subsidies to the South for climate reasons, but that's because they get economically affected as well, if only because of damage to capital of companies that are owned by shareholders in the rich countries. So cross-ownership plays a role in deciding subsidies too. And cooperation, so you can do some game theory analysis of the North and South to decide, you know, when it's good to cooperate or defect. Hint, it's good to cooperate. And things like the Paris Agreement, when Trump, you know, unilaterally withdraw from the Paris Agreement, the Americans were saying, you know, we elected the worst president ever. Nobody can do worse. And then the Brazilians are like, oh, hold my caipirinha, please. And finally, issues of migration. So there's a population dynamics in the model that has to do also with employment and where economic opportunities are better. So you have some economic migrants, but then you need to add the impact of climate migrants. So again, another politically sensitive topic, because now think of, you know, it's not 5,000 migrants marching from Honduras to your border, it's 5 million or 50 million. So the government of Canada has kind of a secret project where they estimate what they would do if there was 50 million people coming up north, and if they can allocate resources for that. Yes, I'm at the end, so now the only last thing left for me to do is to say happy birthday, Bruno. This was in 2008, so he can see a picture of his young family there, and he's busy at work here. I believe the thing that happened next, he saw an island that he wanted to buy, and he was checking the price. And what happened next, you cannot see in the picture because I participated. He proceeded to take his shirt off and swim to the island, and then I also jumped and swam and see, because if he's going to buy an island on the spot, I want to be there to see it. It's going to be another Dupire story. So that's the end. This was in 2008. Angra dos Reis. Angra.
Okay, we have some time for a quick question. Yeah.
So, Matheus, when you think about, let's say, the development of those policies, so last week we had this article on ProPublica in the New York Times about the unintended consequences of the push for, let's say, palm oil and as an alternative to fossil fuels and such. So you say that once you try to optimize something for that, how do you stop that optimization to going out in
So I don't know enough about the details of that particular policy, but I mean, I think the clearest thing that you can do is a uniform price for carbon, and then you look for alternatives in whichever technology you have. So it could be, so this backstop, which in the model is just the one technology that has a price that decreases in time, could be a combination of things. It could be wind, it could be palm oil, it could be whatever it is to replace carbon. But that's the point that you don't need to do. So I'm a free marketer in this sense, right? So just put a price on carbon and let the smart people who innovate and find the best technologies to do that. I don't think you need to necessarily subsidize one particular type of technology because, yeah, you never know about the unintended consequences and so on, picking winners and that kind of stuff.
Okay. Jan?
I was just wondering whether, because what you're doing now is you're sort of have a thought experiment designing a policy and then simulating things and seeing what's the effect.
Yeah.
Is there a way to just put a control on the system and then do some sort of massive nested Monte Carlo to try to numerically actually solve for optimal control as opposed to just guessing the...
Yeah, you're right. One could do that, but we haven't tried that yet. But Ben Bolker also gave the same suggestions, like what Jim was saying. Yes, smart people think alike, so the questions look similar.
I see that you're trying to make some kind of counter-argument for using the SGE models for this kind of problem, but are your equations derived from an agent taking optimization in some sense, or is it like, here's a dynamical system and I'm simulating it? I mean, is there something agent-based?
Yeah, so it's more like the second. So I don't think, for several reasons, both mathematical and behavior, that rational decision agents is a good way to do macroeconomics. The mathematical reason for that is that it's a nil-poles question, and the problem in the way that George defined is not a stable problem by heterogeneity of agents. And then they need to do representative agents. And then between doing a representative agent model and doing something that is much more empirical and based on actual flows of transactions, I think both are, neither is justified from first principle because a representative agent is not coming from first principle. So I prefer the one that matches the data better, which is this kind of model.
So, should we break now, or should we open up the table for? We can open up the questions to all three of them now, since we just took a few at the end of every talk. And does anyone have questions for either Jim, Matheus, or Guillaume? Okay.
Well, still for Matheus, because it's also a question that I asked to Gael many times. When you look at, those, the weakness of all those dynamic models is that when they drift towards the extreme, like you have, those big collapse, etc., the behavior of people changes completely. So is there any way we can, describe certain zones where something different happens? It can be extreme either, by your reaction toward that, or on the contrary, going to wars and things like this.
Yeah. So there are some models, not with climate, but economic models like that, where close to the interior equilibrium, the equations are the ones that I just described. But then when you move away, then there's some nonlinearities, boundary nonlinearities that can play a role. For example, some models that have for the labor force, then you start to have, there's this issue of the employment rate having to remain below 1. So there's a hard boundary in that. But it could be for now just immigration. So now people come in because the productivity of the country is so high, and then it attracts people. And right, yeah, so I'm just giving an example that you can devise models that look exactly the same around the interior equilibrium, but when this extreme things only happen at the boundary, and make it integrated, and that is somehow more natural than having to switch the model, switch the behavior entirely.
Other questions? I had one for Guillaume, actually. So in the fixed point algorithm, you take a simple model, invert to obtain parameters, and then put that into the more complex models, and then iterate and correct the parameters. But doesn't that require the parameters in the simple model and the more complex model to actually to be the same somehow, or at least the same dimension? And how do you deal with that?
Well, simply because the simple model, you choose it, right? So you can pick any simple model you want as long as it's simple. But so for example, if we have I don't know 50 observables, we choose to first parameterize the local vol with 50 breakpoints, if you'd like, placed in the right place.
Okay.
And then the simple model, yeah, you choose to just be a simple model based on the same parameters. Yeah, but that's
So
that.
it does require
You choose it carefully. But the point is, you don't necessarily have to have a great accuracy for the algorithm to work. And also, the good point is you could also choose where you spend your time. So, for example, you could have a model that a proxy that works quite well, and then over time you could still improve the proxy. So you could still throw in some stochastic volatility. Every time you throw in something, you get a little bit better, and you have the options to do that, but you don't have to do that.
Any last final question before we go for our break? Okay, well, let's thank all three speakers. Thanks again.